Okay, so I would like to welcome everybody on the afternoon session after the lunch. The first speaker today afternoon will be Andreu Llabrés from Arctic University of Norway, and he will talk about the differential invariants of curves in G2 flag varieties. So please.
Thank you. So yeah, indeed, I will speak about differential invariants of curves in G2 flag varieties. And this is a joint work with Boris Kruglikov. I would like to thank the organizers for giving me the opportunity to speak in this Scream workshop. Here you have an outline of the talk. So the aim of the talk is to give differential invariants of regular and parameterized curves in G2 flag varieties. The first part of the talk will be devoted to computing Hilbert function that they encode the number of invariants that we have for curves of constant type. And we will assume that curves have always constant type. Then after that, we will focus on the maximal level and the minimal level that corresponds to integral curves. And these curves, they are minimal orbits of the action. They correspond to minimal orbits of the action of G2 on the jets of curves. And these differential invariants were already computed by Doubrov and Zelenko. But anyway, we will revisit them in a different way. And at the end of the talk, I will give a correspondence that we have between curves that is induced from the twistor correspondence between G2 mod P1 and G2 mod P2 via G2 mod P12. And this will allow us to relate all three equivalence problems for all three choices of the parabolic subgroup P. Here we have the root diagram for G2 in three different versions, depending on the choice of the parabolic subgroup. So each choice of the parabolic subgroup gives us a gradation that is illustrated here by these parallel lines. This gradation induces a filtration. In each case, we have that the filtration is invariant with respect to the parabolic group. This parabolic is illustrated by green in the pictures, and in black, we have the negative part that corresponds to the tangent to our homogeneous space. In particular, we see here in the first diagram that we have a rank 2 distribution. So I will here. And we see that it has growth vector 2, 3, 5. Whereas in G2 mod P12, we have also this rank 2 distribution that has growth vector 2, 3, 4, 5, 6. And in G2 mod P2, we have contact here. So for each of these geometries, we have some invariant structure with respect to G2. For G2 mod P1, which will be denoted by M, we have a rank 2 distribution, pi. And as we said, it has growth vector 2, 3, 5. We also have a Nurovsky conformal structure given by this representative. And this gives us the null cone that we will denote by N. For G2 mod P12, we have these coordinates. Well, in all three cases, we have these coordinates that are not the same, but in the case of M and M hat, they are aligned in a way to give us a natural projection from M hat to M. In M hat, we also have a rank to distribution given by delta. And we also have null cone N hat that is induced from the conformal structure that we have in M. Finally, in K, that is G2 mod P2, we have a contact structure and a cone field gamma of rational normal curves given by this ideal. So now let's start with G2 mod P1. We want to give the number of invariants. So we can take a point in M, and P1 will represent the stabilizer of this point under the action of G2. Then we denote by JK M1 the space of K-jets of unparameterized regular curves. And when we take the fiber of this bundle in the first jet over the point O, we get an identification with the projectivization of M, that is G mod P. And we do this because we have a nice bijection between the orbits of the action of G2 on K-jets of curves and the orbits of the action of P1 on K-jets of curves with a fixed point. And we will use the latter action for computing the number of invariants because the dimension is lower, so the computation is easier. As we said, we will assume that the curves have constant type, so it means that at any point of the curve, the first jet belongs always to the same P1 orbit in the projectivization of M. Then some more notation, dt is the dimension of this orbit. And then the corresponding curve of type T will be given by 4 minus dt first order equations. And this gives a submanifold that we will denote by epsilon t, and it has codimension 4 minus dt. Then when we prolong this manifold, we get a tower of bundles in K-jets. And when we count, it's for the number of invariants, it's the counting of dimension of codimension is useful to give these numbers. We have the notation SK here for the codimension of the orbit of the action of G2 on K-jets of curves, and it coincides with the number of invariants of order K. Then when we take difference of two consecutive SKs, we get the number of invariants of pure order Ks. So since G2 is finite dimensional, then at some point this HK that encode the Hilbert function will reach the dimension dt at some order, and it will stabilize at that point. And this is what we see here in the rows of the table. Here these numbers are HKs for each case, and it stabilizes precisely at the dimension dt. So you have here the types of the orbits. So in the lowest level, we have orbits tangent to distribution pi. And the decomposition into orbits is what you would guess. You have distribution pi, it's derived. We also have the null cone, and then we have unrestricted curves. Then when we count the number of invariants, since the action of G2 is transitive, we don't find invariants of zero order, and then you don't expect as well on first order to have invariants because you have dimension 9 jet space, and the group is 14 dimensional, so it's bigger. But then at order 2, we find some surprises. We have here a group of dimension 14 acting on 13 dimensional space. You wouldn't expect invariants, but indeed there is one. And we mark by green the places where we have unexpected invariants. We can do the same for the other two geometries. For G2 mod P2, the decomposition into orbits it's as well what you would guess regarding the G2 invariant structure that we have in here. But then in G2 mod P12, we have these types of orbits that correspond to the composition into orbits of fair sets. And you have some conditional relative invariants, some invariants that, for instance, H2 and H3 that are relative invariants inside delta 3 and delta 4 respectively, but they are not invariants outside. And in the lowest level for integral curves, we see that in G2 mod P12, the first invariant that we get is of order 9, and then it's already stabilized. So at higher order, we just have one new invariant. And similar situation for G2 mod P2, but starting at order 10. Now we focus on M. This was the description for the number of invariants. Now we compute the actual invariants first for integral curves, and then we will go to generic curves. So the first invariant is of order 10. We will denote it by I10, and it's given as a ratio of relative invariants, R10 and R8 to the corresponding powers, and have this expression. So R10 is a really big expression. This is computed directly with PDSolve in Maple, but then we can massage it a bit to get this shorter expression in terms of R8, involving the total derivative operator dx restricted to the equations for pi. Then, as we saw in the table, we have this first invariant I10, and in the literacy sense, if you have we have this invariant, then the next one is generated applying an invariant derivation to this invariant, and the new invariant will be of order 11. Then we apply again invariant derivation, we get the next invariant, and we get the whole algebra of differential invariants. So the invariant derivation that we have is this one, and it gives this theorem for the algebra of differential invariants that is micro-local, this version, because we have a root here, but by the Kruglikov-Lichagin global theorem, we can make these generators rational, and then we will get the global version of the theorem. For generic curves, we have that the first invariant that we get is of order 2, and this we can get by direct computation, but then the next invariants are much difficult to find. So this is again a ratio of relative invariants to the corresponding powers. We have R1 and R2. And then for the next invariants, we construct a canonical frame along our curve gamma that is adapted to the filtration. I'm not going to give the construction of this canonical frame, but let me comment something on that. We have that for the construction, we start with the vector x that is tangent to gamma. And it gives only direction, but we can normalize it using the differential invariant I2. We normalize it by taking the derivative along x of I2 is 1. And then the next vector field that we construct in the frame is y, that it belongs to pi, and it's obtained by conformal duality of x. So we're talking about generic curves, so x doesn't belong to the first derivative of pi. So we can take x mod pi square, and it corresponds to g minus 3, and that is a conformal dual identification with g minus 1, where y lives. Then this frame is invariant. We can fix the metric. Then we have the gram metric with respect to g expressed through the invariant I2. And with the Levi-Civita connection, we generate more invariants. But we have to be careful with this because we have a conformal structure, and first of all, we live in our curve. We can only differentiate along the curve, and then we have to be careful when we conformally change g. We have to take this into account. But if we do that carefully, we obtain the next invariants: 2 of order 3, 4 of order 4, and this together with this invariant derivation, where now dx is the unrestricted total derivative, we get the whole algebra of differential invariance for generic curves. Now we have the algebras for differential invariance in the generic case and the integral case for G2 mod P1, but we can make a correspondence to know something about the algebras in the other geometries. Because we can view M hat as a prolongation of M. M hat is a collection of pairs of points in M and points in the projectivization of pi. And similarly for G2 mod P2, we can take a prolongation, and it's again G2 mod P1, 2, but with different coordinates, and we will denote it by k hat. And it's a collection of pairs of points in K and points in the projectivization of the rational normal curve. Then we find a diffeomorphism that changes the coordinates in these two descriptions of G2 mod P1, 2. As for the structure that we have here, we already talked about delta. Then delta tilde is essentially delta, but in other coordinates, because delta is a Rank distribution that is split. So we have two differentiated lines, and what phi does is to interchange these generators in a way that when they are interchanged, then the projections pi L and pi R are very natural. So delta doesn't project to pi, but it first derived is dimension, it's rank 3, and when we projectivize, we get pi. And similarly, delta tilde, its third derived is dimension 5. When we take projection, we get dimension 4, and we get the contact structure. And this twistor correspondence gives us also correspondence between differential invariants of integral curves. We just need to specify a point in the fiber for the lift. We have our algebra of differential invariants in here in G2 mod P1. And then we have an extra coordinate in M hat, well, in the minimal level in delta, restricted to delta. So we have to specify this coordinate, and it is given by R equal to Q1. And similarly for the other side, we specify the coordinate. And as you see, the order changes. We have orders 0 R and first order Q. And this is because, as we saw in the table, the first order invariant of G2 mod P2 and G2 mod P1 is at order 10. So this is mapped to a lower order and the same in a similar way. We have that these leaves are right inverses of the projections, and these projections are very natural, as we discussed earlier. As for generic curves, the correspondence is not like this one, because here we have that the algebra of differential invariants is the same in the three geometries, but here we have different number of invariants. But still, we can find some correspondence between curves. On the left side, we have a leaf that is one-to-one, and this is given by a line that, so we have a one parameter family of lines that span pi upstairs in M hat. And if we align this with y in the canonical frame that belongs to pi, we get this extra coordinate r that we need for the lift. And on the right side, we use also considerations on distinguished curves and the fact that through any point in the projectivization of the context structure, we have a line that that is second to the rational normal curve gamma and intersects it exactly at 2 points. So when we take these intersection points exactly at the point given by the upsilon x that is aligned on D, so it's a point on the projectivization of D. This gives the lift for the right side. So as we see, the computation of differential invariants on G2 mod P1 gives us already a lot of information of the invariants in the other geometries. Thank you for your attention.
Okay, thank you. So now we have short time for questions or comments, either from here or from Zoom. Is there anybody from Zoom? Ah, here.
Yes, just a question. Did you touch differential relations between these invariants of curves, like recurrence relations? You looked at it, I guess, no?
Sorry, like what?
The recurrence relations between the invariants you showed us. Did you look at it? In principle, you have them for free, essentially.
So, sorry, I don't understand the word, the reconciliations.
So in the works of Lee and Oliver, you have infinitely many differential invariants. And by applying the invariant differentiation operators you showed us,
yeah,
you find some relations between them. Did you compute this algebra or look at it?
No, there's no relations because it's ODE, right? It's one invariant differentiation.
Can you hear what?
Something, even in case of curve. Anyway, it's simple. I know. It was just a question. Okay.
I mean, we don't work in paradigm of Fels or Euler. We work in paradigm of kind of Lee tracer, right? So we finite number of invariants. We don't present infinite number of invariants. Invariant derivation generates everything, so we don't need a recurrence relation. Yes, because we just get all generators from invariant differentiations.
Okay. So, are there any other questions? If it is not so, we shall continue in 5 minutes. So we are 5 minutes behind the schedule with Denis. So.